So welcome everyone, and thank you for joining us. My name is Marie-Lise, and I will be your host for today's AI Research Bite session. This series of short and informative talks showcase cutting-edge research work from ServiceNow AI Research team. The AI Research Bites are open to all, especially those interested in keeping up with the fast-paced AI research community. Today's session features a 15-minute talk from Oleksiy Ostapenko on specialized and efficient LLMs and will be followed by a 10-minute Q&A. Before we begin, let me share a few words about today's speaker. Oleksiy Ostapenko is a research scientist here at ServiceNow AI Research in the AI Deployment Program. He holds a PhD in Compute Science from Université de Montréal and Mila, and his research focuses on continual learning, modularity, and language models efficiency. With that, it's my pleasure to hand it over to our amazing speaker. Up to you, Oleksiy.
Thank you. Okay, let me share my screen. Thank you for the kind introduction. Hi, everyone. Thank you for having me here. So today we'll be presenting some work on making language models more specialized. And the quick disclaimer here, everything covered here is part of ongoing research work. And so why do we want specialized models? Well, short answer is efficiency. So generalist models are expensive to run, and most of their capabilities go unused for many specialized tasks. So a medical diagnosis system doesn't really need to know how to write poetry or how to write songs or music, right? And so the key question I will target here is how do we build domain-specific models without wasting computational resources and money, as well as how do we do it with efficient adapters without compromising data privacy. It's at least some form of data privacy. And so in the following, I will give you an overview of two papers that both work towards this end of specialization and enable it in different ways. And both of these works also target specialization at different stages of model development. So the first work, which is about data scaling laws, targets specialization at the model pre-training stage, which is usually expensive and slow. And the second work, which is about sparse adapters, targets the post-training stage, where we're interested usually in fast and lightweight model adaptation. And so if there were two things to take away from this presentation, I would like those to be the following two. So number one, first work can help save money by avoiding costly mistakes when it comes to selecting domain-specific pre-training data. And number two, sparse adapters can enable efficient model specialization in the post-training under some form of data privacy constraints. So I will now highlight the motivation, main ideas, as well as some key results from both of these works, starting with the first one, titled Using Scaling Laws for Data Source Utility Estimation in Domain-Specific Pre-Training. Okay, so how do we specialize language models in pre-training? So pre-training usually consists of at least two phases, and this figure shows a typical learning rate schedule of a pre-training run. So on the x-axis, we have the token count, and on the y-axis, we have the learning rate. And so first phase is performed with a constant learning rate usually, and the model is trained on general large-scale text data. So for example, in our experiments, we trained a 7B Mistral-like model and trained it for around 1 trillion tokens on a mixture of FindWeb, Edu, and Dolma datasets. And then in the second phase, so the second phase is called annealing. And here the learning rate is decayed linearly from the base learning rate to 0. And so in our experiments, we run this phase for around 330 billion tokens. And this is where the domain-specific data is usually injected. So in our experiments, we start injecting domain-specific data at this red star, which is around 50% into the annealing. And this gives us a stable checkpoint and also enough runaway to test different data sources. So again, this red star, this is where we inject usually high quality domain-specific data sets, data in our pre-training data. And so what is the use case that we're targeting in this work? So consider an example of a pharmaceutical company that builds a language model for, let's say, drug discovery. And so they can evaluate the effectiveness of their model in public or private benchmarks, but they still need billions of tokens for effective domain adaptation. So far more than what they actually already have in their proprietary data set. So they have to invest in data acquisition now. And so what are their options? So roughly, they might have the following options. They can filter open source data sets like PubMed, probably one of the cheapest data sources. They can generate synthetic data, maybe chemical data using models like GPT-4 or other LLMs, more expensive than filtering. They could also invest in just buying data sets or even human annotation. So human annotation would be very expensive. And so the key question here that we target here, how can they decide which data source to use? And so a common approach towards data source selection for domain specialization and pre-training is relying on short annealing experiments on candidate sources. So the right plot here shows an outcome of such an experiment that we ran at low compute. So the y-axis is basically showing the performance improvement due to injecting that domain-specific data at that red star that we've seen at the beginning. And we take data here from 3 different sources. So these different sources are depicted with this different dots, different colors. And then, so usually the money is invested into acquiring more data from the best source, assuming that data source ranking will be basically preserved also at larger compute or at larger token count. And so here we see that it's definitely looking like the green data source is better than the other ones. So the green data source, by the way, is a form of synthetic data augmentation here using other LLMs, so quite expensive data source. And so the key question we're asking here is, can we be sure that ranking induced at low compute will also hold at higher compute? And so in this paper, we showed that indeed the data source ranking is not invariant across compute. So as you can see here, ranking changes completely at larger token count. So here the pink source actually outperforms the other ones at higher compute. And I would like to stress again that data source selection is a high stake decision because investing into wrong data source can easily waste hundreds of thousands of dollars. And so here this plot demonstrates that relying on single point estimates can be dangerous indeed, and that data source utility has to also depend on the compute. And so in this paper, we propose a simple method of estimating such a compute-dependent data source utility function. So in a nutshell, the methodology we propose here is, as depicted in this figure, to run multiple annealing experiments with varying compute or varying token count, varying investment, and then fit a scaling law and use that scaling law, which is depicted with dotted lines here, for data source selection. And so in the manuscript, we demonstrate on 2 domains that this framework can be used to prevent costly mistakes when it comes to data source selection. So to summarize, when it comes to specialization in the pre-training phase, we always face this question of which data source should we use to mine that domain specific data. And so the question isn't really which data source is better. The question is more like which data source is better at a given scale. And so data scaling laws can give us this tool that can help us answer the question which data source is worth investing into before scaling up that investment and before potentially losing a lot of money. And so the immediate practical value here is preventing those costly mistakes by investing into wrong data source. So now I would like to move on to the next part, and I kindly ask people interested in further details about this work to refer to manuscript directly or also to contact me later. So data scaling laws help us to choose what data to train on in the pre-training stage. Now in the second part, I will now focus on model specialization and post-training phase. And in post-training, we're usually interested in having a lightweight specialization procedure. So, and we will achieve this using parameter-efficient sparse adapters. And so this work has been conducted with colleagues from McGill, UDM, Mila, Georgia Tech, ServiceNow, and Microsoft. And so more specifically, we will focus on the question of how can we enable transfer across specialized and independently post-trained models without data sharing. So this work targets the following use case scenario. So imagine a company that wants to train specialized models on customer-specific data or maybe on customer-specific tasks, but they cannot mix this task or customer-specific data sets into a single pool. In other words, data sharing is not permitted. Maybe because these data sets arrive sequentially, so there is some kind of continual learning involved. But they still want to have a single model that has some knowledge about all of these tasks or domains. In other words, cross-task knowledge transfer is desired here. And so currently the most popular solution to this setting is to train low-rank adapters, so-called LoRAs, or to do full fine-tuning also, so fine-tune the whole pre-trained model on these separate training data sets from all of these separate tasks or customers. And this will give us basically a library of specialized adapters. And then to obtain a single model with shared knowledge from all these specialized adapters or models, they are usually merged through some form, some flavor of parameter averaging. But the problem is that this merging does not really work always, right? So merging can degrade significantly the performance of the resulting model when we combine multiple LoRAs or multiple pre-trained models, fully fine-tuned models. And so in this work, we hypothesized that sparse adapters can do better at learning each of these tasks, but also at merging. So what are sparse adapters? So as opposed to LoRAs, whose updates are to the underlying language, pre-trained LLM are low rank but dense, sparse adapters perform sparse updates. So they first select a small subset of trainable parameters from the underlying pre-trained LLM, and then they only update those parameters. So basically, we hypothesize that sparse adapters can work better than LoRA when actually learning the task, because maybe of the lottery ticket hypothesis, essentially, but also after merging because of potential less parameter interference due to their sparse nature. So to this end, we experiment with 20 training tasks. So we train a separate sparse adapter per task. And we then evaluate the performance on held-in tasks. So basically on held-in test sets of the training task, but also on the held-out tasks, which are completely unseen tasks. And so our baseline here will be LoRA full fine-tuning, multitask training. So multitask training permits data merging, while other methods will perform model merging. So in terms of results, we first look at the performance on the held-in tasks without merging. So here we assume that we know which task we are testing on, which is the form of Oracle routing. And so on the right plot, the y-axis here is the performance, the x-axis is the percentage of trainable parameters. And so two things can be highlighted here. First, sparse adapters actually outperform LoRA here and even full fine-tuning. And second, the sweet spot for sparsity is around 99%, meaning that only 1% of weights are actually updated, which highlights the effectiveness of these adapters at high sparsity level. Now let's look at the performance of the merged model. So here we perform just simple parameter averaging. For sparse adapters, this procedure is a bit more involved, but I'm not going to go into the details there. So on the held-in tasks, merged sparse adapters clearly outperform LoRA. But when it comes to generalization to unseen tasks, their performance is more or less on par. It's also worth mentioning that there is still a big gap to multitask learning baseline. So again, multitask learning baseline, especially on the held-in task. So multitask learning baseline permits data sharing, whereas other baselines do not. And so I guess it's not a magic. I guess there is a real performance cost to preserving data privacy here, not sharing data between models. Finally, another interesting observation that we make here is that block sparse adapters perform similarly or even sometimes better than element sparse adapters. So block sparse adapters use structured sparsity. That is, they select and update contiguous blocks of parameters. So this is interesting because this can result in more efficient merging of multiple adapters on the fly in certain scenarios. This is due to better hardware efficiency because GPUs can better handle block operations, more efficiently handle block operations. So we can make use of specialized kernels for block sparse matrix multiplication. So to summarize, the immediate practical value of this work is that it can enable fast and lightweight model specialization, but with also data private cross-model knowledge transfer. We also show that sparse and block sparse adapters can serve as performant alternative to LoRA. Weight interference when merging is still a key limitation here. So basically when we merge these adapters, when adapters overlap, their updates can conflict each other and degrade performance. So future work can explore sparsity patterns that minimize overlap. For example, orthogonal sparse adapters is an interesting future direction. Also, training techniques that can make adapters more compatible with merging is also another interesting direction for future work. So this is the end of the presentation, and just to reiterate on the two key takeaways. So number one, data scaling loss, which we covered in the first part, can help reduce risk of wasting money due to selecting wrong data source in pre-training or domain specialization. Number two, sparse model adapters can enable efficient and data private model adaptation in post-training. And they offer an interesting alternative to LoRA. So thank you for your attention. Now